talk about sound. Sound is a mechanical, longitudinal wave that requires a medium such as air or really any solid or liquid or gas to travel through. Sound is classified into three different categories, which really has nothing to do with physics and everything to do with how the human ear works. And infrasonic sound is a sound that is too low pitch for us to hear. For your average human, infrasonic sounds are less than 200 hertz, less than 170 hertz. It varies a little bit from ear to ear, but not too much. Then you have audible sound. That's the stuff that any human can hear, and generally that's 200 hertz up to 20,000 hertz. This varies with age by a great deal. At this point in my life, I'd be surprised if I could hear above 13,000 hertz. When you go to the nurse's office and they have those little beep tests where you put on the headphones and then they do the beeps and you raise your hand if you can hear it in either ear, those are testing whether or not you've got the normal range of human hearing. But be careful with the word normal. Ears are pretty different and they do deteriorate with age, typically losing higher frequencies first. So a teenager can probably hear up to 25,000 hertz if they haven't spent a lot of their life listening to really loud music and stuff. By the time you hit your 20s, that's probably closer to 20,000 or maybe even 18,000 hertz. And by the time you hit your 40s, maybe you're down to 12,000 hertz or maybe even less, depending on what you do. Protecting your ears is a good idea because right now, when you damage those nerves in your cochlea, we don't know how to fix them. But anyway, 2,000 to 20,000 hertz is about it for audible sound, because those are audible for most people. Above 20,000 hertz is ultrasonic. There are lots of animals that can hear some ultrasonic noises. Dogs can hear up to 30,000, 32,000 hertz. Cats can even hear up to 60,000 hertz. They can hear extremely high-pitched noises. This allows them to hear the super high-pitched noises made by tiny little critters that they're going to want to hunt and eat. The frequency of sound corresponds to its pitch. A lower frequency noise tends to have a lower pitch, and a higher frequency noise has a higher pitch. These are very related but different topics. Frequency is objective and measurable. It is the number of compressions per second, compressions and rarefactions per second, the number of waves that pass by or pass into your ear per second. And everyone who measures that frequency will agree on it. Pitch is how your brain interprets frequency. And we may or may not agree on whether or not something is high pitch or annoyingly high pitch or whatever. Pitch is entirely inside your brain. And so that is subjective, and you can get into some interesting conversations like, how are we even sure that we're hearing the same thing? With similar physiology, we probably are, but we can never be absolutely sure. Similarly, intensity is related to loudness, but they're not the same thing. Intensity is defined as the pressure per area of your mechanical wave, like your sound wave. So when I'm speaking right now, I'm creating air pressure differences with my voice box. But if you get further and further away from me, that energy spreads out as you go. And so the further away you get, the less intensity there is. However, that translates into less loudness as well, generally, but people hear differently and brains work differently, and even you could, after a loud concert, for example, everything was really loud in there, and then you go outside and everything seems quiet. But you even could go from a very quiet room into that same environment and think everything was loud, because your brain kind of interprets loudness based on how loud things were before you enter into that new environment. And so loudness is subjective, and it is not objective. Intensity is objective and measurable. I know this is the sound video, but intensity with light works in very much the same way. When you have a light bulb and you held it right up to your face, it's really bright right in your face. It's very intense. As you move away, the light spreads out over the surface of a sphere, so it spreads out and it decreases as 1 over r squared. That intensity is how much power per area is hitting, and it's related again to brightness, but same idea. Go from a very dark room to a dim room, and the dim room seems bright. Go from a bright room into that same dim room, and it seems very dark. Brightness is subjective and happens in our heads, whereas intensity is measurable and objective. So, Anyway, back to sound. Something you don't need to know is the decibel scale. Decibel comes from two words. One is deci, meaning tens, and bell comes from Alexander Graham Bell, one of the least favorite human beings of deaf Americans, and also the inventor of the telephone. Those two things are not related. 0 decibels is in theory the quietest sound you can hear. That's called the threshold of hearing, and it's an insanely tiny number. It's 1 times 10 to the minus 12 watts per square meter. A square meter is really big, right? Your eardrum is this big. That's a tiny fraction of a square meter, and 1 times 10 to the minus 12 watts per square meter is just a ridiculously small thing. That's a vibration of less than the distance of the molecules of the air themselves. And that's the quietest noise that your typical human ear can hear. On the other hand, the threshold of pain is about 1 watt per square meter. That's 1 trillion times more intense. And so the threshold of pain is literally where things start to hurt. In terms of decibels, the threshold of pain is somewhere in the 140 decibel range. That's really loud. In terms of sound, you are probably one of the first generations who are going to have worse hearing than your parents. And it's almost entirely due to the advances in technology for earbuds and headphones. People listen to music way too loud. Amazingly, people will go do something loud like mowing the lawn. You're supposed to wear earplugs and or ear muffs to make that sound quieter. And what a lot of people are doing is they're just putting in earbuds and then turning them up. Well, remember that loudness is subjective. So when you're in a loud environment, everything seems quieter after a time. Your ears literally get tired. And so you turn it up more, and then your ears get tired and you turn it up more, and your ears get tired and you turn it up more, and eventually you're literally vibrating the insides of your ears apart. You're damaging the nerves. And it turns out that really loud sounds like a shotgun blast or something like that at close range can damage your ears a little bit. If you do it often, then that can really damage your ears over time. But much quieter things like 80 decibel noise, that's like traffic, subways, things like that, those can over time really damage your ears too. And the vast majority of people listen to their music over those levels. They listen to it at greater than 110 decibels. And that's crazy. Stop doing it. Right now, modern technology, once you've damaged the nerves in your cochlea, we don't have a way to fix that. You're going to lose hearing starting at the high end, and it's going to go down from there, and there's nothing we can do to stop it. So we don't have to know a lot about the decibel scale, but you should know that you're almost definitely listening to your music, your movies, everything else too loud. You're damaging your hearing, and you should really do something about it. What sound does a car make when it goes by? Meow. Right? But what sound does the car make when you're in it and you drive by someone? It just makes a constant noise. It makes a constant noise. But a person listening to the car approach hears something higher pitched, and listening to it move away hears something lower pitched. That's the Doppler effect. That's not in your head. That's a real effect. Let's see if this works. I've got myself a tuning fork. I've got myself a string. I don't know how well my phone speaker will pick up the Doppler effect from this, but let's give it a try. What do you think? Higher pitch coming towards you, lower pitch moving away. Why is that? Well, if you think about water waves, think about something bobbing on the water. When it's bobbing on the water, those waves make circles. The waves are traveling at the same velocity in every direction, and so you get circular waves moving away from the object. But if that thing starts to move as it's bobbing, then the center of the new circle is shifted towards one side and away from another. It bunches up in the direction of motion, and it spreads out in the other direction. And if your wavelength is bunching up, that means your frequency is going up. If your wavelength is spreading out, that means your frequency is going down. So this Doppler effect is a very, very noticeable thing. Regents, you need to know the idea. AP, you've got to do the math. What does that math look like? It looks like this. In this case, be careful, this FO is not F naught. It is the frequency of the observer. So it's the frequency observed is equal to the frequency of the source times a ratio. That ratio is the speed of the wave plus the velocity of the observer divided by the speed of the wave minus the velocity of the source. Now, some people find it easier to rearrange like this because that groups the observers and the source. And so let's do a quick example.
On a 24 degrees Celsius day, a train is moving at 40 meters per second. It sounds its whistle at 500 hertz. What sound would an observer hear as the train approaches? And what sound would the observer hear when the train is moving away, if in both cases the observer is stationary? The first thing we need to do is find the speed of sound, which is 331 meters per second plus 0.6 times the temperature of 24 degrees Celsius. We get 345 meters per second. Next, you just plug your numbers into the Doppler Effect equation. We've got 500 hertz and 345 meters per second, the observer is stationary, and the train is moving at 40 meters per second. We get 566 hertz. Notice that that's about a 10% change, and the train is moving at about 10% of the speed of sound. This works just fine for an approximate answer most of the time, but if you want to be precise, you have to use the formula. Also, take a look at this negative sign. If students make a mistake, it's almost always here. And whether or not this needs to be positive or negative, you just have to ask yourself, does it make sense? This negative sign will make the denominator smaller, which will make the frequency higher. That makes sense, so that's correct. When it's moving away, we do the exact same thing, and in the denominator, we get this minus 40 meters per second is also negative. Again, ask yourself if it makes sense. Minus minus is positive. That's going to make the denominator larger. It's going to make the frequency lower. So yes, it makes sense. Some students like to write a plus or minus rather than a minus and a plus in this equation, and then apply whichever one makes sense by thinking about it ahead of time. In that regard, how you do it is a matter of taste and entirely up to you.
And by the way, while we do the math with sound, you could do it with light, you could do it with water waves, you just need to know the speed of the wave. On that note, it's really easy to notice with water. We can certainly hear it with sound. Do we see it with light? If you run at someone, do they become more blue? Well, technically they actually do, but two things. Our eyes aren't sensitive enough to pick that up, and we're just not moving nearly fast enough. The Doppler effect is approximately proportional to the percentage of the speed you're traveling. It's the percentage, that speed's percentage of the speed of the wave. And light is just so fast that everyday things just don't move that fast. But Edwin Hubble looked around the universe at other galaxies in the early 20th century. He looked around and he found that those galaxies were shifted, they were redshifted away. That means that they were moving away from us. The light from the spectroscope showing your colors for hydrogen were shifted a little bit too far to the red. And the further away they are, the more they were shifted. And this was the beginning evidence for the Big Bang Theory. He looked around the universe and said, everything is moving away from us. And then they did some math and said, okay, everything is moving away from everything else too. It's not like we are the center of the universe. It looks like everything used to be the center of the universe. And so if you could click rewind and watch the universe, if everything's moving away, they'd all get closer and closer and closer. They must have started off together and separated somehow. That's the beginning of the Big Bang. So the Doppler effect with light is not something you're going to observe on Earth with your eyes. But it's absolutely something that we can observe using computers. In fact, radar uses radio and the Doppler effect in order to figure out how fast things are going and to some degree in what direction. So computers are fast enough to do it, but we certainly are not. However, we can observe it in space because some of the speeds we're talking about are so extraordinary. On a final note, please take a few minutes, it's about 12 minutes long, and watch this video by Vihart called called What's Up with Noises. It's a really great video that sums up a lot of what we've talked about, and she goes a little deeper into the timbre, that is the quality of the sound, and it's a really neat video. She's both a mathematician and a musician. She calls herself a math musician, and she's a great YouTuber. Her channel's a lot of fun. So please take a moment to watch this. It's really great. And then we'll move on to light.